Good morning, ladies and gentlemen. I'm John. What? Aren't you part of this?
I'm Haley.
And we're here to talk to you about Why am I sitting in this chair? Much better. We're here to talk to you today about the PMXDB.
PMXDB.
What? This is something that I created years ago. Had just started working for a company, and I wasn't getting enough mix design. Or it's right before I started working for a company. I wasn't getting enough work in the lab. I wasn't getting enough, brain stimulation. So I started making up these fake clients and these fake specifications, and then designing mixes off of those. So this is the first of many. And let's just dive into it. We're looking at the concrete mix design, and the way that I created it was for you to be able to use, it's almost like a choose your own adventure. Mm-hmm. Right, and ACI 211, which we can't show, we will create the tables for you at home, but you can buy it online. It's not that expensive. It is expensive. But everything that we need to go through this step-by-step approach is available to us in this adventure that we have. We've just got to choose the adventure. And that's the thing. There are many ways to create a concrete mix design. You just have to figure out the direction you go and recognize that this is only a benchmark. So ACI 211 feeds off of something called the absolute volume method. And what that absolute volume method means, if I could draw it out for you here, is that we have a certain volume that we're working with. Here in the United States, it's a cubic yard of concrete, 1 cubic yard, which equals 27 cubic feet, right? Because a cubic yard is 3 foot by 3 foot by 3 foot, which is 27 cubic feet. So that means I have all this volume to use up. Now, what am I going to do with that volume? We didn't really use a method like that. We used this different method, but using ACI, wow, that was a little chunky there. ACI 211 gives you a standard guideline to design or choose what to use. Okay. And this is bookcrete. But what do we know about bookcrete? Can we go direct?
Not the same as labcrete.
And not the same as realcrete. So this gives you, and that's what I'm stuttering over here. This is not the labcrete. This is definitely not the realcrete. Okay. Right? This doesn't take into account size of the aggregate or the dirtiness of the aggregate, the number of fines.
Temperature or weather.
Nothing. The type of cement, the cementitious that you're using. And it even has guidelines in here for that the use of water-reducing admixtures, ASTM 494, may also be used to reduce mixing water by 5% or more. So what they're insinuating is that's not in here, not taking that into account here. Okay, so looking at your information, why don't we go down? We have a non-reinforced slab on grade, 6 inches thick, exposed to severe freeze-thaw and de-icing. Compressive strength must be around 4,000 or be at 4,000 psi, and that's supposed to be at 28 days. And I want you to design a cubic yard and 2.25 cubic feet. So that question that you asked before about how do I go from pavement to lab, you're going to do that. By the end of this, you're going to know how to do that.
Sweet.
Yeah. Okay, so the next piece of it is the type of aggregate we have. And this is really important. We are going to make certain assumptions about the cement and other things, but with the aggregate, that's key ingredient here. No pun intended. So we give you the absorption, the moisture content, and the specific gravity of the aggregate, which you need for the design, as well as the dry rotted unit weight. And remember that because reason why I give you the rock first is because that's what we design with first. We come back and design with sand later on, and we have the information for that, the fineness modulus, or the FM of the sand, the specific gravity, the absorption, and the moisture. So all that information that we need, we're always going to look at here. All right, so let's get into it. So we get into ACI 211. You're on 211.1-7, step 1. It's table 6.3.1, and it asks you, or asks you to make a decision, based on the type of construction you have, the minimum and maximum slump that you're looking at. Now, this is assumed to be slump without admixtures or additives.
Okay.
So we're going for a total water cementitious ratio design, if that's what you want to call it.
Sure.
But it's not with admixtures. So the thing that we're looking at are pavements and slabs, and that's what we're designing. So our decision, so if we look at a pavement, we see maximum of 3 inches. So if we go, and it says maximum 3, minimum 1. So what I called it there was 2 inches plus or minus 1 inch. So this is step 1. So here what you could do is, if you want to be picky, I mean, you can always say that, hey, I know my industry and a 3-inch slump is not what I need. I'm going to choose to bump that up, especially if the requirement is a lower strength. You could always make that decision, but you know what I say is the first 100 passes that you take through this, you follow it to the letter.
Okay.
You make the mixes in the lab, you make your adjustments from there, but keep this as the level playing field. So I said 2 inches plus or minus 1 inch. Then step 2, you're going to be using this humunga table right here, and it is an awesome table, and it goes back to a few things here. First, your maximum aggregate size, which if we look back at our notes, our maximum aggregate size is 1 inch. We're using a 1 inch maximum MSA river rock. Now, we're also working in a severe freeze-thaw condition. Now, what does that mean? So for severe freeze-thaw conditions, we have to use air-entrained concrete.
Oh, yes, sure.
So, first of all, going back to this table, this is where we were at. Right? Coming to this table, the first thing is we have a 1 inch maximum sized aggregate, so we're in this column.
Okay.
Right? Then we have to decide, are we non-air entrained or air entrained?
Trained.
And because we're in severe freeze-thaw, that's back in our notes right here, so exposed to severe, right? We're in the air entrained, just like you said. So we all of a sudden come down to here. Now the question is, what is our slump? And we said 2 inch plus or minus 1 inch. Now, if I was on the higher strength side of that, I would choose closer to the 1 inch. But because I'm on the lower strength side, I'm going to choose 3 to 4 inch slump. And that's what this column is, right? So 3 to 4 inch slump. So we're on this second level. And when that comes to is to your water, and that's what this gives you, based on your maximum sized aggregate, your required slump, or the slump that you want, you're going to use 295 pounds per cubic yard of water.
Cool.
Now here's the thing. There's a trick in this question. So we've got our 2 inch, we got our size, maximum size 1 inch aggregate, absorption 1%, blah, blah, blah. The water that we use, we said it was, I said it was 270, so that was the 1 to 2 inch. So let's go back and say it's 1 to 2 inch,
Sure.
right? So we say 2 inch plus or minus, so we'll use 2 inches. That's 270 pounds of water, but we end up subtracting 25 pounds. Why did we subtract 25 pounds?
I don't know.
If you go back to our notes, we are using a river rock.
Okay.
And with that river rock, if you go into your notes section, rounded aggregate will generally require 30 pounds less water for non-air entrained and 25 pounds less for air entrained concrete. So we can either use crushed rock or rounded rock. So if we use crushed rock, we would have to stay at that 270,
Sure.
right? Sorry about that, 295, 270. So we go 270 minus 25 pounds, so now it gives us 245 pounds of water. Now, there's another piece of information that we need from this,
Okay.
and that is our air content. Now, if you look at the bottom of the table here, you have all these different exposures to freeze thaw,
I
mild,
remember this.
moderate, or severe. So we, according to our notes, are severe, right? So we go to severe, and guess what?
6%.
We're at 6%. So now, we've gone through this non-reinforced slab on grade, exposed to freeze thaw and de-ice, severe freeze thaw and de-icing. Now we're going down to the compressive strength must be at 4,000 psi, and that's supposed to be at 28 days, right? So that's the next step, and that's here in table 6.3.4a. So we say, okay, we want to be 4,000 psi. Now here's the thing, there's two ways of going about doing this. You could say it's either 4,000 psi, or you can say it's 4,000 psi plus 1,200 psi saying that we've never used this mix before. And it seems like here I'm choosing to go just with the 4,000 psi. But if you wanted to do that, you can jump to the 5,000 psi or even use linear extrapolation to say, well, I want 5,200. Sure. But for us, we're going to go 4,000 psi, and it's air entrained, so 4,000, that's non-air entrained, there's air entrained. So we're at a 0.48 water cementitious ratio. So strength 4,000 psi, we got our air over there at 6%. Strength at 4,000 psi, we use our table, and it says 0.48. And then they have you do a check. They say maximum permissible water cementitious ratio for concrete in severe exposures. Are we in severe exposures? Yep. So why do you think that they're doing that, Haley?
To just cover their butts.
Yeah, durability wise.
Yeah,
you make a porous concrete in a high MAC chloride, high freeze-thaw environment, it's going to go to SHIT. So it gives you 4 different categories. Structural wet continuously or frequently exposed to freezing and thawing, or structure exposed to sea, water, or sulfates. So it's more freeze-thaw. We do know we're in the Denver region, so we're not seawater, we're more exposure to freeze-thawing. Now, this is for a slab on grade that's 6 inches thick. Are we a thin section?
No.
Are we a railing?
No.
A ledge?
No.
Ornamental work? No. Not ornamental. Less than 1 inch cover over steel. Because we're non-reinforcing. So we're all other structures, and the maximum we can be is a 0.5.
Okay.
Where are we?
0.48.
Boom. So, are we good? We're good. So that's our next check off.
I miss this.
Right? Well, you get to do this all the time. So that's 0.50. We're good to go. Okay, so the next thing that we do is we decide a very specific number that we need from this table 6.3.6 to determine the volume and then the weight of our coarse aggregate.
Okay.
And that number is called the volume of coarse aggregate per unit volume of concrete. Isn't that an amazing number?
Yeah.
And it's based on a number of things. First of all, the maximum sized aggregate, which we know is 1 inch. So there's our 1 inch. And then it gives us our fineness modulus here, right, that we have to use. And our fineness modulus, I believe, of our sand was 2.85. So we have this 2.4, 2.6, and 3.0. And there's 2 things that you can do. You can either say, hey, I'm going to use linear extrapolation and I'm going to determine what it is to the 0.001. Or you can say, well, I have 3.0 and I have 2.8. What is my number closer to? Is it closer to 2.8 or 2.85?
And what are we?
Or 2.8 or 3.0, and our value was 2.85.
Okay.
So we're definitely closer to the 2.8, which here I believe is 0.67. Now, we used 0.66, and I believe that was from linear extrapolation. Either way, it's again what you're more comfortable with. And again, please bear in mind that there's a certain correction factor that you always have to be aware of, because this is not where we end up, is not bookcrete or labcrete. Where we end up is
realcrete.
And if you're making a decision between 1 and 10 pounds, that decision might be made for you better on some days rather than on other days. And that was one of the biggest mistakes that I ran into, because I was always like, well, I need 1,704 pounds. And the batch plant guy was like, what are you talking about, dude? I can't guarantee that.
Yeah.
I could guarantee 50-pound increments.
Yeah.
So or whatever it was. So just be aware of that. So from this table, we got this 0.66 value, and bear in mind, so this is the volume of oven dry rotted coarse aggregate per unit volume of concrete for different fineness moduli of fine aggregate. Do you know what that means? Yeah, I mean, I have to oftentimes say this to myself over and over and over again.
So it's, you have your concrete,
right?
You have your aggregate,
right.
But it changes for your FM,
right?
Your aggregate.
So there's a certain pace to aggregate ratio that we want to keep.
You don't want it too high or low.
You don't want it to. So again, this gives you a starting point. It's based off the dry rotted unit weight of the aggregate,
Okay.
the size of that aggregate, and the fineness modulus of your sand. What's the definition of fineness modulus? Do you remember that? I think it's the FM or the FM. It's the number 2. The fineness lambda is an empirical figure obtained by adding the total percentage of sample of an aggregate retained on each of the specified series of sieves and dividing the sum by 100. And this is about the sand. So the fineness modulus of sand is the cumulative percentage retained on specified sieves. So here you go. So here is, they go from a number 4 through the pan, and they're just doing the weights retained divided by 100. Yeah. So here.
Easy.
So again, you're taking into account, something from both aggregates. Now, if you look at Oklahoma State University, what is Tyler's software package, the Tarantula?
Oh, tarantula curve.
That is a little bit more specific. There's also a product called Lisa product, and you could just do it yourself. Look at different aggregate to paste or paste to aggregate ratios, find where you like, and then when your aggregate changes, you can make those changes based off of the porosity index that you're getting from the new aggregate and the paste content that you liked, or the paste to aggregate ratio, or vice versa. So anyway, getting back to this as we digress, now that we have that initial information, we can get back to our absolute volume method, 27 cubic feet. So you always got to remember that's how much we're working with. So the first thing is we've got our water, and we knew we had 245 pounds per cubic yard of water, so we divide that 245 pounds per cubic yard by the unit weight of water, which is 62.4 pounds per cubic feet, giving us 3.92 pounds or 3.92 cubic feet out of
Cubic yard. 27.
27 cubic feet. Correct. After that, we've got to look at the cement. Now, we're not looking at fly ash yet.
Okay.
We'll get into the nitty gritty of that. No pun intended. I don't understand the pun. If there was a pun.
Gritty.
Oh, rock. It's funny. But looking at the cement, the first thing we have to do is determine how much cement we have.
Okay.
And we do that by taking our weight of water divided by our water cement ratio, which gives us 510 pounds per cubic yard.
Okay.
Now, to get the volume of that, we have to divide that pound per cubic yard by our unit weight of cement. Now, our standard specific gravity of cement is 3.15.
Okay.
So 3.15 times 62.4 pounds per cubic foot gives us a unit weight of 196
6.6.
pounds per cubic foot.
Okay.
So when we divide 510 pounds per cubic yard, right, by 196.6 pounds per cubic foot, we end up getting 2.6 cubic feet per cubic yard. Now, the next thing is we've got to figure out, so we have the water, we have the cement, and I'll number these. Cement, let's go to air. So with air, we know we have 6% air. How do we turn that into cubic feet? Well, if we have a 27 cubic foot volume, cubic foot per cubic yard volume, and we say we have 6% of that is air, we literally just get
Divide by
6%, divide by 100, and multiply by 27 cubic feet per cubic yard. And that gives us 1.62 cubic feet per cubic yard. Now, going back up to coarse aggregate here, we have our 0.66 volume of oven-dried, coarse, rotted, coarse aggregate per unit volume of concrete for different FM, fine aggregate. So we take that 0.66 and we multiply it by 98.5 pounds per cubic foot, which was information given to us earlier, that 98.5 pounds per cubic foot dry rotted unit weight. So we multiply that by 0.66. Now that only gives us pounds per cubic foot. but we've got 27 cubic feet per cubic yard here, so we end up getting is, multiplying that by 27 cubic feet per cubic yard, and we end up getting 1755 pounds per cubic yard. And then from there, to get the volume of that, we divide that 1755 by the specific gravity of that rock, which was given to us as 2.62 times 62.4 pounds per cubic foot, which gives us a unit or a volume of 27 cubic feet for our cubic yard of concrete. Now, when we add all of those up, the 3.92 cubic feet per cubic yard of water with the 2.60 cubic feet per cubic yard of cement, and our 1.62 cubic feet per cubic yard of air, and our 10.73 cubic feet per cubic yard of aggregate, we get a total of 18.87 cubic feet per cubic yard that is used up. So that means left over we have 27 minus 27 cubic feet per cubic yard minus 18.7 cubic feet per cubic yard, with a leftover of 8.13 cubic feet per cubic yard of sand. So to get our weight of sand, we take that 8.13 cubic feet per cubic yard minus the specific gravity of our sand given to us earlier, which is 2.6, multiplied by 62.4 cubic feet per cubic, or pounds per cubic feet, to give us 1,319 pounds per cubic yard of sand. What we could have done is, instead of using that method, we could have used the first estimate of weight of fresh concrete, which, if we have a 1-inch rock and it was air entrained, we start out with 3,850 pounds, and we just start, removing from there. And I personally just don't like that method, but ultimately, through those calculations, we end up with a final design weight of 245 pounds per cubic yard of water, 510 pounds per cubic yard of cement, 1,755 pounds per cubic yard of our river rock, 1,319 on our sand, pounds per cubic yard on our sand. And because we have 6% air, I suggest 0.5 fluid ounces per hundredweight of an air entraining agent. And then, more than likely, because we want a 3-inch slump, a 2-inch slump, I think it was 1 to 2-inch slump, we might not need to use a mid-range. But if we are going to use a mid-range, we would use 2 fluid ounces per hundredweight. Okay, so the next piece of this is we have these weights of our aggregate, and we have this water content, but that is just bookcrete. It's not labcrete or realcrete. And what we have to do is take into account our moisture content and our absorption, not only for the weight of the aggregate, but also for the batch water. So what we're going to do is use the information given to us. So for our coarse aggregate, we had an absorption of 1.75%, or we had a moisture of 1.75%, and for our sand, we had 6.3%. So to get our moisture-laden weight of rock, we take 1,755 pounds per cubic yard of our rock and multiply it by 1 plus 1.75%, which ends up being 1.0175, which gives us 1,786 pounds. We do the same thing for sand, multiplying 1,319 pounds per cubic yard times 1.063, or 1 plus 6.3% divided by 100 to give us 1,402 pounds. Now that's going to be our new weight of rock and sand respectively. The next thing that we have to do is take into account the free water. If you have your rock here, your rock is going to have pores in it. The absorbed water is going to be the weight of water that the rock absorbs into its body. So that's absorbed water. And then the moisture content is just going to be that absorbed water plus whatever water is on the surface or supersaturated on the surface, and the moisture content minus our absorption is this free water that's going to immediately contribute to the batch water, and if it's not taken care of, will ultimately contribute to a water of convenience. So what we end up doing is taking our 245 pounds per cubic yard, this is our design water, and using our information given for our rock and our sand to determine our batch water. So we take our 245 and we subtract it by 1,755 pounds per cubic yard times the quantity, 1.75% minus 1%, and obviously those are divided by 100. And with that, calculating all that through, you'll find that your new batch water is going to be 163 pounds per cubic yard. Now, please bear in mind, I called those two separate things. Your 245 pounds per cubic yard, where we originally started, that is your design water, and where we ended off, taking into account the moistures and the absorptions of our aggregate. We have a new batch water, what will we use in our batch, of 163 pounds per cubic yard. So our estimated weight for a cubic yard of concrete is 163 pounds per cubic yard of water, 510 pounds per cubic yard of cement. Our coarse aggregate is 1,786 pounds per cubic yard. Fine aggregate is 1,402 pounds per cubic yard, to give us a total weight per cubic yard of 3,861 pounds. So that was fun, because we just got it done. Hopefully you learned something. Let us know if you have any concrete questions. I feel very robotic.
You're acting very robotic.
Let us know if you got any concrete questions or concrete concerns. Pretty excited for this project, so let us know your feedback. We're doing this for you.